Principle of work and energy. Let's consider a point that is moving on a curved path. Let's say this is the curved path. Let's expose all the forces that act on this particle which has a mass m. We have the sum of all forces along the tangential axis. Also we have the sum of all normal forces along the normal axis, and of course the resultant forces, which is equals to Fr, also equal to the sum of all the forces. The particle travels from point, let's say this is S1 to point S2, and let's show the small differential displacement, or distance rather, and this is its velocity. First, let's consider the equation of motion for the particle along the tangential direction, and that would be Ft is equals to MAT. Let's substitute the equivalent of tangential acceleration. We know that A ds is equals to V dV, and this acceleration is tangential acceleration. So now our equation becomes Ft equals m V dV over ds, and let's transfer ds on the left side. That would be Ft ds is equals to m V dV. Now let's integrate both sides, and for the limits let's assume S1 and S2 for the distance or displacement, Ft ds, and V1 and V2 for the velocity. We can integrate the right part of the equation. Let's continue. That would be S1, S2, Ft ds, which is equal to, of course, that would be 1/2 m V2 squared minus 1/2 m V1 squared. Note, however, that summation of forces along tangential, looking at this diagram, is also equal to summation of forces cosine theta. Here, you just attach cosine theta on that, and that becomes summation of tangential forces. And if we substitute this one, it becomes S1 S2 F cosine theta ds is equals to 1/2 mv2 squared minus 1/2 mv1 squared. Now the left part of the equation seems familiar, and that is equal to the work done from point 1 to point 2. It is equal to work from point 1 to point 2, which is equals to 1/2 mv2 squared minus 1/2 mv1 squared. This equation represents the principle of work and energy. The term on the left side is the sum of all the work done by all the forces that are acting on the particle as it moves from point S1 to point S2. While the two terms on the right side are the particle's final and initial kinetic energy. Sometimes they are labeled as T sub 2 and T sub 1. Like work, kinetic energy is a scalar, and it has a units of joule in metric system and foot-pound in FPS or English system. But unlike work, which can be either positive or negative, take note that kinetic energy is always positive. The kinetic energy T is always positive, regardless of the direction of the particle. So the final expression of this form is often like this: T1 plus this is equals to T2, which states that the particle's initial kinetic energy plus the sum of all the work done by the tangential components of all the forces that are acting on the particle is equal to the particle's final kinetic energy. So that is the meaning of this equation. So is there any situation in which this equation does not apply to, or what is the limitation of this equation? And the answer to that question is it does not apply to any body which is in motion which loses or increases its mass. For example, spaceship or any spacecraft. A spaceship, as it departs the Earth now, as it moves from the Earth to other extraterrestrial objects such as the Moon, the spaceship loses a significant amount of mass. It loses a tons of kilogram of fuel, so the mass is not constant. And that poses a problem because this equation does not take into account that consideration, which is, of course, the mass is changing. And you can verify that if you can trace our derivation. The mass is constant, as you can see here. But of course, this equation applies to all types of forces, may it be magnetic, electrical, whatever type of forces that are acting on the body, as long as the tangential component of that force is considered. And it also applies to all types of motion, whether it may be constant motion or uniformly accelerated motion or none of those types of motion, because the kinematic equation that we used in derivation is fundamental. So the only limit to this equation is that not apply to moving bodies whose mass is changing. Okay?